Okay, so the Zilog 80, better known as the Z80, was an early microprocessor based off of the Intel 880. However, it had a number of advantages, such as an expanded instruction set and a lower price point than the 880. In fact, the reason that it was so similar was because it was designed by former Intel engineers who actually worked on the 880 while at Intel. The Z80 was first released in 1976 and had originally been designed for industrial use like warehouse robots and other business-to-business platforms. One of its main advantages is it was still compatible with the 880 with a number of key advantages. There was a number of different versions, for instance, with different clock speeds. There was built-in DRAM, which allowed it to be able to process more data at once. It was slightly slower than the SRAM, but it was cheaper. So once again, it was cheaper than the Intel 880. But unlike the 880, which only had single byte instructions, the Z80 was able to have multi-byte instructions, which is how it was able to have a much larger instruction set. So this was because it utilized all 256 instruction slots when some of them were wasted with NOP instructions, which did nothing on the 880. So this was a game changer in the microprocessor world. Okay, so here is a diagram of the Z80's data lines as well as address lines and a number of other different pins that we're not really going to worry about at the moment. So what we are going to notice, though, is that there are 8 data pins as well as 16 address pins. So we've actually tied down half of the address pins. So it normally would be a 16-bit system, but we've made an 8-bit system on our system. So right now we can access 255 unique data addresses, normally 256 because that's 2 to the 8th, but since we start counting at 0, it's one less than that. If we'd used all 16 bits, however, we could have accessed up to 65,536 memory locations, but once again, it's one less than that, so 65,535 since we start counting at 0. Okay, so to zoom out for a minute, here is the full architecture of the Z80. So at its core, like any microprocessor, it's just moving bits around. And in order to do that, it has a lot of things like instruction registers, instruction decoders, control logic, but then it also has a set of registers as well as muxes. But in this case, we have 2 sets of registers. The regular set, which is the letters without an apostrophe after it, and then we have an alternate set of registers with the apostrophes. This allows the Z80 to almost multitask. So you can switch all the data from one set of registers to another and use and keep them there while you do some other task in the other set. So that's a very good way, which was kind of revolutionary at the time, to be able to move things around like that. And then you have a number of other things like the ALU, where certain math equations are done, and then a number of other things. But right now we're going to focus on these registers. Okay, so for our intents and purposes, I'm using an emulator. Here's an example. I'm going to do is just going to fill up the memory just to kind of show you how it works. So we have a memory editor here. So as you will see when I assemble and load the code, it's all right here. You can see the program. And you can put it in either decimal or hex. Right now I'm using hex, which is why I have the H at the end. Now, normally in the actual Z80, you wouldn't do it this way. It would be in binary, but in this editor allows us to do different ways. So here you can see the registers and what's in them, the different instructions, the clock cycles, stuff like that. And then here you can see the memory. So let's get that going. So as I said, I assembled and load, and then I will start the simulation. And you will see it's going to start down here. You can see it's moving around, moving memory around, just moving bits around as we discussed. I'm going to put it up a bit faster. As you can see, it's just doing it. And there we go. So that's just a quick example. So we are now going to talk about a very powerful opcode, which is called LDIR. LDIR stands for load, increment, decrement, and repeat. This is a powerful opcode which is able to perform in one command what would normally take many more, and it blew away the minds of the Intel engineers who had never thought of this. They obviously would eventually use this for newer computers, which is why in modern processors we have many such commands, but this was the start of it. So it basically works by allowing programmers to make self-modifying code. So in this case for the Z80, it will work by essentially copying an entire block of code contained in an address specified in the HL register to the location specified in the DE register. And then another register, BC, is used to specify how many bits to copy from the memory locations that were specified before. It's very similar to building a bridge in Minecraft, where you will have to put out each block ahead of you so you know exactly where to go next. So that's kind of how this works, and then it propagates itself through the memory as much as you tell it to. So we'll have a demonstration of that coming up. Okay, so starting with the HL register, let's talk about how this works. So in this case, we're actually coupling together two 8-bit registers, the H register and the L register, and this is going to make a 16-bit register. And since this is a 16-bit register, we can have the size of the memory that it's pointing to. So remember, it points to a location in memory, and we can have that block of code in that memory location be up to 64 kilobytes long, because 1 kilobyte equals 1024 bits. And remember, this is 16-bit, so we can move a lot of code. So then this is going to be the location of where that is in the memory. Okay, so next we have the DE register. So once again, this is two 8-bit registers coupled together. And this is where we put the destination of where we want the memory that was pointed to by the HL register. This is where we want it to be transferred to. So that location will be stored in these registers. And once again, since we have it as 2, it's 16 bits and can store a lot of data, which makes sense since HL is also 16 bits. So yeah, this kind of shows where we want to put the next block if we continue using our Minecraft bridge analogy. Okay, so now we come to the final register pair, which is BC, which is once again two coupled 8-bit registers, and this is going to contain the bit counter, which is kind of why it's good to use BC. So here, this shows how much memory we want to transfer forward. So we put in the number, and it gets decremented each time until it reaches 0, and then it gets refreshed after it has gone to 0, at least in the code that we're going to use, so that it'll keep going throughout the entire memory, and then it'll loop back around, but we'll talk about that later. So here's BC. Okay, so here's the code we're going to use in our LDIR example. So line 1 is where we're loading HL with location 6. So this is a pointer, so it's going to point to location 6 in memory, and we have to put the H there to show that it's in hex, because in this emulator you can do both hex and decimal. So anyway, that's the location where the data is stored, or the beginning of it is stored. And then register DE we're loading with 11 because that's where we want to start loading the data. So kind of using our Minecraft bridge analogy, that's where we're putting that first block of where we want to go. And then BC is how much we want to copy, right? Because we don't always want to copy everything. And so then we have to remember that DE and HL will be incremented and BC will be decremented until it reaches 0. And then we're going to have to refresh it, kind of like a capacitor, but with numbers instead of electricity. And so that's going to happen whenever it reaches 0. So right now it's at 5, so after 5 it'll get refreshed back to 5 so that it copies through the entire memory, and then it will wrap around, but we'll talk about that later. And then these are just the things with the apostrophes there, and with the semicolons, those are just notes, so the interpreter will not read this. And then we have the code LDIR, which takes no specific inputs, it just knows what to do based on the previous commands. And yeah, that's how it works. Okay, so here's an example of the LDIR code working. So we have load HL with, in this case, we're using hex, which is why we have the H. So we load in this address, address 6, then address 11, and then we have the last 5 bits, right? So it's only going to take the instruction before, because we don't want to do all the instructions. That would mess it up. Okay, so now I'm going to assemble and load. So you can see it's in memory here. And I'm going to put the do slow, and then I'm going to start the simulation. So as you can see, it's starting to overwrite the memory. And as you can see, it's going in a pattern, as it should. I'm going to put the rate up much faster so you can kind of see how it looks. So you can see it worked, and then I'm going to stop the simulation. And as you can see, here is the first 3 lines, and then it does LDIR, and then it loads the BC again, which is refreshed back to 5 because it goes, so it'll count down to 0. So see 5, 4, 3, 2, 1, 0. So reloads it then, and then as you can see, it keeps going. Okay, so as you may or may not have noticed in the last example, if we had let that code continue to run, it would have continued to overwrite the memory locations. And that's kind of how this machine works because it's limited. Since we only have an 8-bit machine, there are only a total of 256 memory locations. And this means once it reaches that final location, it'll roll back over to 0, 0. But since it also starts at 0, 0, the numbering, I mean, 255 is the highest memory location you can have, but it's only the 256th place. This is similar to the odometer of an old car. Once it gets to 100,000 miles, it rolls back over to 0, and there you go, you got a new car. So that's how that works. So now you may ask yourself, why are commands like LDIR and other semi-automatic commands useful? Well, they're useful for a number of ways, but a big one is that it makes the code more efficient, and this can help save the programmer a lot of time, since they won't have to write a loop every single time. But these commands are also especially useful with the Z80, because even with its max memory being hooked up at like a 16-bit machine level, that's only 64 kilobytes of memory, because 2 to the 16th is approximately 64K, and that's really not that much. So if you really want to squeeze as much functionality as you can in there, you got to do little shortcuts like this. But this is especially has many uses in programs where you need to move blocks of code around many times, like let's say you're making a video game and you want to move the sprite across the screen. Well, if you know where that sprite code is, you can just have it moved using the LDIR as opposed to having to write a long loop. But also, these have evolved over time. So, for instance, these are still in modern CPU opcodes. It's just different. But so, for instance, now there are separate memory controllers that will do this stuff instead, or maybe even a core of the CPU, so it doesn't have to take up core time. But so this is still very useful even in modern code.